Dear students, so how to formulate the stiffness matrix for a CST element? Let us discuss in this lecture video. So this is the problem statement. Determine the stiffness matrix for the constant strain triangular element, that is CST element, which has its coordinate positions as follows: 100, 100, 400, 100 and 200, 400. The coordinates are given in the units of millimeter. Assuming plane stress condition, it is asked to formulate the stiffness matrix. The properties are given as Young's modulus as 210 gigapascal, Poisson's ratio 0.25 and thickness of the element as 10 millimeter. So first I have converted the Young's modulus value from gigapascal to Newton per mm square, because for determination of stiffness matrix, first we have to convert all the parameters into a single unit. Okay, we know the expression for stiffness matrix K as B transpose dB into A into T. So here B is the strain displacement matrix, D is known to be the stress strain relationship matrix, A is the area of the element and T is the thickness of the element. Okay, first we are going to determine each elements of this formula, and finally by simply substituting all the elements and by performing the matrix multiplication, we will be arriving at the desired stiffness matrix expression. Okay, so T value is directly given in the problem as 10 millimeter. So to find out the area of the element, we can use this formula: 1 by 2 determinant 1 x1 y1, 1 x2 y2, 1 x3 y3, where x1 y1, x2 y2 and x3 y3 are the coordinate positions of the given CST element. So just by simply substituting the coordinate positions, we will be arriving at the result of area as 45,000 millimeters square. Next we can calculate the strain displacement matrix using this formula. So here the term A, that is area, has already been calculated. So the elements of the strain displacement matrix can be calculated using the known formulae. So here Y2 is the Y coordinate position of node 2 and Y3 is the Y coordinate position of node 3. All the coordinate positions are represented in the figure and given in the problem. So just by substituting the respective coordinate positions, we can calculate these values. After calculating these values, just by substituting those values in the B matrix formula, we will be arriving at this result. Next, we can calculate the stress strain relationship matrix. For plane stress condition, the formula for D is E by 1 minus nu square. The matrix 1 nu 0, nu 1 0, 0 0 1 minus nu by 2, where E is the Young's modulus and nu is the Poisson's ratio. So the D matrix for the present case will be like this. So now we have calculated all the required elements to generate or develop the stiffness matrix K. So we have calculated the B matrix. So here the first element in the K matrix formula is B transpose. So this is the B transpose matrix. This is B matrix. This is B matrix into area into thickness. So in the first step, we can calculate all the constant values out of the matrices. So that is 1 by 90,000 into 224,000 into 1 by 90,000 into 45,000 into 10. So the value is 12.4444. Okay. So for simply multiplying the matrices, first I have kept the first matrix as it is and I have multiplied the second and third matrices. Okay, and in the next step I have multiplied the remaining matrices. The size of the stiffness matrix of a CST element is 6 cross 6. So with the aid of the stiffness matrix, under loading condition, we can determine the displacement positions using the general finite element equation F is equal to K into U.